lecture 28, more scheduling algorithms. We're also going to talk in this topic about idling and priorities and multiprocessor scheduling. But when we left off in the last part, we said, there's some scheduling algorithms, and we talked about, I believe, 6 out of 10 of them. And, well, now we should go back and finish the remaining ones, right? So, one of the ones that was left was highest response ratio next. Responsive design, kind of a big deal. And for this, what we're interested in is something called normalized turnaround time. And we've covered already what turnaround time is. This is the total time it takes both for execution and waiting. But normalized turnaround time is the ratio of the turnaround time to the service time, which is to say, the time it takes to execute. The thinking behind this basically is that we can tolerate longer processes waiting for a comparatively longer amount of time, right? If it is going to take several hours to run a particular task, it's okay if it has to wait an hour before we start it. That's just kind of how things go. It is, however, extremely frustrating if something is only going to take 2 minutes and we have to wait several hours before it starts, right? So this sort of thing is important. And for this, we have this measure of normalized turnaround time, which helps us to identify basically like how far off target we are. And the goal is to minimize the normalized turnaround time not only for a given process, but actually to do it for all processes if we can do it. And to do this, we're going to calculate value R. R is this ratio. It is W plus S, so the waiting time plus the service time divided by the service time to give a particular ratio. And the service time is, as always, a guess in this situation. Again, it could be a user-supplied value in some circumstances, but typically it's not. So we're just going to take a guess at it. And this is calculated for each process. When it's time to select the next process to run, we choose the process with the highest R value. So W plus S divided by S produces some number. It could be greater than 1 or less than 1, but whichever one has the highest absolute value. And a new process has a value of 1.0 at the beginning because it spent no time waiting, and therefore it may not be very likely to be selected. Depends what's happening, of course, in your system. And jobs that are short, i.e. they have a small value of S, are likely to get scheduled quickly, right? But things that are much larger, well, they might not get scheduled quickly, but it depends on how much they wait. And this approach introduces something new that we haven't had before, and this is the concept of an age of the process. Right? The term W indicates how much time a process has spent waiting, and a process that has been waiting for a long time will rise in priority while it's waiting. It doesn't necessarily go at the beginning and it waits behind other processes that are higher in priority, but over time a process's priority increases, which is helpful, right? It means process A, if it's got a very long service time, its waiting time will eventually climb to the point where it gets a chance to run. Even if it's been waiting a very long time, it won't be waiting indefinitely. And that's very important, right? It prevents starvation. And a lot of the schemes that we've talked about so far for scheduling do have this risk of starvation somewhere, right? That a process never gets to be at the front of the line, or it doesn't get enough opportunity, or we just always prioritize the thing that's the highest overall priority, so other processes can starve. But in this strategy, processes will not starve. One of the weaknesses, as you can imagine, is this need to guess for the service time S. It's not easy to predict what it's going to be. A simple guess may be sufficient. You can record statistics, or it doesn't really matter, as long as we have something that vaguely approximates the actual execution time of the process. Okay, the next strategy, multi-levels. All right, here's a chicken sandwich at 3 levels. Those of you paying careful attention will notice, I think actually the chefs have hamburgers in front of them and not chicken sandwiches, because I didn't quite get the images aligned. Oops. It's fine. But I anyway enjoy watching the chefs of different levels attempt various things. But okay, we have different levels. And for the most part, a lot of the strategies we've talked about don't care about priority in the sense of like assigned priority to a process. And that's not good, right? Priorities exist for a reason, and we should be paying attention to it at least at some level. Otherwise, why do we have it? What's the point of saying, oh, this process is high priority, if nothing is high priority at all, right? It might seem very fair, right? This idea of ignoring priority can be actually nice in the sense that nobody's process is treated differently. But on the other hand, this is a computing task. It's not a democracy. So it's not ideal for situations where processes behave differently, right? When a desktop or a laptop has lots of processes running, some of them are visible to the user. You have your web browser open, you have the PDF reader open, you have a chat program open. Those are very visible to you, and you can see their response times, and you care about those. But then there's all kinds of things that run in the background that you are interacting with somewhat less. Right, there's the service that keeps track of what the battery health is in your laptop. There's another service that is going to be responsible for updating your calendar. All those things, they run in the background. We don't see them all the time, and so we don't necessarily want to treat them the same way as a scheduler. We might want to apply different algorithms to different kinds of process. And having a multi-level queue gives us something like that, where we can say, all right, well, if it's in this kind of queue, we will schedule it using this way. If it is in a different queue, we will schedule it a different way. And that sort of thing will help us to achieve all of the goals of the system, even if sometimes that means user processes are prioritized or deprioritized, depending on what makes sense. And so the multi-level queue is really what it sounds like. You just take your main queue for the ready queue and break it up into several of them. And a given process, when it's ready to run, can be in one of the queues, but only one. There are no processes that are treated in both queues, because that doesn't make sense. And which queue it's assigned is based on its attributes. Is it based on the priority, the memory needs of the program? Is it a foreground task, i.e. one that's like user interactive in the UI or the command line, or is it some sort of background service? All those things can be used to make a determination about what kind of process it is, and according to what queue it's going to go into. And that should be relatively easy to implement. And then you have your choices, right? When there's multiple queues, you have to choose what we're going to do with each of them. So the foreground queue could be scheduled by round robin, and the background queue by first come, first served. We could say that some queues have absolute priority over others. If there's something here in this emergency task queue, then we always do it regardless of anything else. Or maybe we have time slicing amongst the queues. It could be balanced evenly. We could give more time slices to things at the beginning, like let your imagination run wild, so to speak, because there are a lot of options, if you will, for what we could do and how it would all work. Right? Everything we've talked about so far, you could apply a piece of it to the multi-level queue kind of system. So here's an example of multi-level queue from also ancient history, but this is a story that has at least a humorous end. And what made this kind of interesting is it was a time-sharing system, so intended for multiple users, and CPU-bound processes were given longer blocks of time to execute so that they would not have to spend so much time swapping. And so things that were in the high priority class, they get one time slice, and the next you get two, third class means 4 time slices, and so on. Why does this work? Again, when we're trying to prioritize, say, responsiveness of the system, we want things to work quickly. We don't want users to wait a long time for getting a response to input, that sort of thing. Then prioritizing short tasks makes sense. and so those are I/O bound processes, so they should be high priority. But things that are CPU bound, we might put them in the third class. So when they run, they get to run for 4 full time slices before they have to give up the CPU. That kind of thing is convenient, right? It's appreciated because it does reduce the amount of time swapping, but it still allows us to prioritize processes that are less CPU intensive and more I/O intensive. Okay, so how do we determine what class a process is? Well, the rule was pretty simple. It starts out as first class, and then if it does run up against the time limit, so time slice expired without there being an I/O that happened on it, then it gets moved down 1 class until, of course, it's in the lowest group and can't move any lower. Okay, so this does mean that the process gets lower priority, which, all right, doesn't always sound good, but I mean, it is sort of how it works. But it does mean that when the process is actually selected to run, it does run for a longer period of time with less chance of being interrupted. Never say never, things will happen, but less chance of being interrupted. Okay, look at a couple of the things that we've talked about so far. This is kind of a ratchet, like it only goes in one direction. So a process can move down in the priority list, but we haven't discussed any way for a process to move up in the priority list. And that sounds like it might not be fair, right? We create a process at the beginning, it needs to do a whole bunch of work to sort of get started, and it uses a bunch of CPU after that, but once that's happened, let's say, in this example, it's an I/O bound process. Well, now what? Because we've set it up as if it is like a very expensive CPU time process, and therefore it lives in the lowest category. Well, what do? We need to find a way for things to go up in priority. Well, it turns out if a user pressed the Enter key, that was a sign that the process was likely to become user interactive, right? The user is interacting with it, and that's a big hint that it is in fact going to be something the user is interacting with in the immediate future. So if they're entering a command or they're like browsing through the data that has been returned or something, it's a hint that this is, well, responding to user commands directly now. So, okay, if that's the case, move it up. But the problem, of course, is that a genius user, and there is always one, if you come up with the system and you think, no one could defeat this system, it's perfect in every way. Unfortunately, life is rarely so nice, and users will in fact find ways to defeat the system intentionally or unintentionally. So one person figured out that by pressing the Enter key repeatedly, his long-running processes would actually finish faster. And as the Scooby-Doo villain always says, we would have gotten away with it too if it weren't for those meddling kids. So that's bad enough, right? One guy has figured out how to exploit the system. It gets worse because, well, he decided to be nice. He told all of his friends. And so with all of his friends knowing that if you press the Enter key, your process finishes faster, well, of course they all started doing it. I mean, why wouldn't they? And now all the benefit of this system was lost because, well, if everything is a priority, nothing is a priority, as I'm sure you know. In which case, well, nothing was gained by having this kind of system that moved processes around priority classes. So, well, just goes to show that clever users can, in fact, upend just about anything if they put their mind to it. Okay. And this scheduling algorithm is referred to sometimes as feedback. And you might have seen in the list of scheduling algorithms, I said multi-level queue and then also feedback. Why is that? Well, the thing is that we are not using any information provided in advance about priorities or runtimes or things because we don't know those, and even if they're user-supplied estimates, they're pretty unreliable. So to use something that is actually a bit more reliable, what we're doing is we give every process, if you will, a chance, and then if we need, we will adjust its priority based on the CPU time it's received so far. And that's a bit more fair, right? We're assigning information and we're assigning priority based on what's actually happened. not based on guesses and not based on assumptions. And a process that's used a lot of CPU so far gets a lower priority. A process that has not used a lot of CPU maintains a high priority. And so there is a certain amount of feedback in the system that determines what is actually the correct priority for this process. So now for something completely different. This one is called guaranteed scheduling, or, in the words of John Hammond, I guarantee it. Okay, what's up with guaranteed scheduling? Well, the idea behind it is promising the user something, and then you do your best to fulfill the promise. The idea is that if we say there are n users, then every user gets an equal share of CPU time. That sounds pretty reasonable, especially for something that's like it's a shared server and there's hundreds of students who are using it at the time. It's not nice, of course, if we end up with one person using a disproportionate amount of CPU time. So yeah, we're happy if we can make it more fair. Alternatively, if there are M processes, maybe you look at it at that level instead of per user, where you say, all right, for each of these processes, each of those gets an equal share of CPU time. So to make that happen, right, the system is going to have to keep track of how much CPU time each process has received and then compare that to the ideal, right? Where the ideal is represented as a value of 1.0, that would be 1 share of the CPU time, and if its actual CPU time is significantly less than that, that this process hasn't received as much CPU time as it should have, and therefore it should increase in priority such that it does get that share of time. Alternatively, if a process has CPU time of double, 2.0, it's an indication that, well, it's received more CPU time than would be fair, so it should have a low priority, meaning that other processes get to run instead. All right, and the slide uses the word should, but should is put in quotation marks. And the scheduling algorithm is to run the process with the lowest score, trying as best we can to keep every process close to 1.0. It's never going to be perfect, right? There's always the possibility that this one's a little higher and that one's a little lower, and those kinds of things are just part of life, because you can't always have everything perfect, but it is going to be a strategy that tries to balance everything as best as it can. Our last main scheduling algorithm that we're going to talk about is called the lottery. And the lottery is a system to give both predictable results and have a simple implementation. I mean, it sounds great. And the premise is basically that every process gets a certain number of lottery tickets, if you will, and when a decision has to be made about, say, which process is going to get the CPU next, well, a lottery ticket is selected at random, and a process that is holding that ticket will be the one that gets the resource. So, okay, anthropomorphizing processes pretty hard, right? Like, processes don't play the lottery, they don't hold tickets, there are actually no physical tickets in this regard, it's not like that, right? But the idea behind this is that the system provides a certain chance of getting a resource, right? If a process has priority P, we don't really have a good definition of what that means or a useful implementation of that. Whereas if we say, okay, if a process has a fraction f of the total tickets, we can expect the process to get f% of that resource. And so if f represents 30% of the CPU time, then, well, we expect that in the long run, given sufficiently random lottery draws, that process will use about 30% of CPU time. When a process is terminated or when a process is created, we can increase or decrease the number of tickets, or we can redistribute them, that sort of thing. And yeah, that's kind of the overall strategy. More important maybe should be in quotation marks here, processes have more tickets and therefore they have a higher chance of winning. If there are 100 tickets outstanding and our algorithm is sufficiently random, which again is a big catch because computers are really only good at pseudo-random numbers. If a process has 25 of them, it has a 25% chance of winning the draw. And if you want to increase the process's chance of winning, you give it more tickets. If you want to decrease, and then it gets fewer. So if we want to increase the priority, we give it more tickets. If we want to decrease, we give it fewer tickets. Unlike the real lottery, though, there is always a winner, and a winner singular in this regard. If you play one of the lotteries where you choose some numbers, there is the distinct possibility that somebody chooses the same numbers you chose, and then you have to share the winning. Doesn't happen with CPU. And similarly, there's also always the possibility that nobody chose the correct numbers this week, and therefore nobody wins, but that doesn't happen with the CPU. And again, it's not that processes go and buy tickets and hold on to them or whatever. It's just okay. The operating system will know that okay, if the range of process A is from 0 to 12, if the random number that is generated appears between those values, well, okay, then process A is selected to run. So don't get too caught up in the lottery analogy. And hypothetically, you could allow cooperation. And cooperating processes could be permitted to exchange tickets. So a client that gives its requests to a server could then, when it submits a request, give some tickets with it, increasing the chance the server gets the resources to run next and respond, which hopefully results in a faster response than if the client process, which is going to get blocked anyway, just sits there holding on to the tickets in the first place. Does it always work? No. But it is still interesting to think about, right? What could we do with an underground economy of tickets, so to speak? Because that might be clever, right? Just a thought. Anyway, the lottery approach is much less overhead generally than guaranteed scheduling, although there is still a significant amount of work to do in terms of assigning which processes get what and doing the random draw. It does prevent us from having to keep track of how much of a resource a particular process has received. All we just care about is what is the current chance, and roll the dice and see who wins. Assuming that the lottery system is sufficiently random, as I've said before, over time allocation tends toward the proportions of tickets that each process holds, and we can change those proportions at any time. If process A has 20%, B 30%, and C has 50%, then the CPU will be given to the process in about that ratio as expected. The big proviso on this is that random numbers are fairly hard to generate. Okay, so this concludes, the remaining 4 scheduling algorithms that we wanted to talk about. In the next topic, we will consider some more advanced things in scheduling.